Okay, welcome to lesson 8.3. In this lesson, we're moving into three space. So we're looking at all the different types of equations of the line in three space. There's vector, parametric, and a new type called symmetric. So we're going to go over vector and parametric first, since they're actually very similar to what you did in two space. The vector equation in three space looks exactly the same. The difference now being that the r naught vector is going to have three coordinate points, x naught, y naught, and z naught, and the direction vector again will have a third coordinate. We're going to call it c. The parametric equations, again, very similar for x and y. It's just the addition of this z equation that we now have, which will be the z naught from the r naught vector plus t times the c from the direction vector. So very similar to space. Note that t can be replaced by a number to find a point on the line. So those are the first two types of equations. We're going to come up with the symmetric equations of the line. I'm going to scroll hold your breath. We're not going to see them yet. We're going to come up with them. And what we do is we just take the three parametric equations and we rearrange them to solve for the parameter t. So I want to make each one of these equations look like t equals some stuff. So I'm going to bring the x naught over and subtract it. And then I want to solve for t, so I'm going to divide out the a. And this is the first symmetric equation. So I actually don't memorize this or anything. I'm just going to think about my parametric equations and rearrange them each time. So again, I can do the same thing here for the y equation. I'm going to solve for t, so I'm going to bring the y naught over and subtract it. And then to solve for t, I'll have to divide out the b value. And that would give me the t. And then I'll do the same thing with the z equation here. Solving for t, I'm going to bring the z naught over and subtract it. And then to solve for t, I need to take the multiplier of c and divide that out. And so these three equations, notice that they're all equal to t. So instead of having a t involved, I can just say that these three things on the left are equal to each other, and that's what I have here. X minus x naught over a is the same as y minus y naught over b is the same as z minus z naught over c. Where a, b, and c cannot be 0 for each of these. And so remember that a, b, and c are part of my direction vector. So what we're saying is that the direction vector can't have a 0 in it for me to write an equation like this. Remember that the x naught, y naught, z naught will be numbers, and the a, b, c will be numbers. And so I'll just be left with these three variables x, y, z when I fill in these equations. All right, so our example 1, we're going to come up with the vector, parametric, and symmetric equations of the line passing through, and we've got three different pairs of points and three different equations for each of those. So these three pairs of points were selected to show us something different in each example, but we're going to come up with all 9 of these. So remember that to come up with the vector, parametric, or symmetric equations, doesn't matter which one, you always need to have a direction vector. So I'm going to start each of A, B, and C by finding a direction vector. So for part A, my direction vector, I can use A to B, or I can use B to A. It does not matter. I'm going to go A to B. Just out of habit, I do the first one to the second one, and then I'm going to go negative. So to come up with the new coordinates of my direction vector, I'm starting with the b coordinate and subtracting the a coordinate. So I'm going to come up with -2, -1, and -9. And then I can come up with the three different types of equations for this line. When you do this and there's multiple types of equations in one question, make sure you label each one for me so I know which one you think is which is important to me. So for the vector equation, it's going to be r naught is equal to, r is equal to r naught. Now remember, for r naught, I'm just picking a point on the line. So I can pick A or I can pick B. So again, when I mark this test, the vector equations are going to look different for everybody. There are 2 possible points that can come first here. I'm going to pick A, but you could pick B. And then we're going to add, we're going to create a parameter for this one. I'm going to call it t for the first one, and I'm going to multiply it by that direction vector that I came up with. And then I'll just define that t is an element of this set of real numbers. All right, so we've got our vector equation. Next, I'm going to move into the parametric equations. So this is the one where we're separating out, and it's all based on this vector equation really. I'm just coming up with now an expression for x, y, and z. So for the x coordinate, I'll take the x coordinate if I were to like multiply the t into this vector and then add those coordinates together. So -1 minus 2t, and then the y will be the 3, and then it's going to be -1 times t, so minus t. And then for z, that is a z there. Taking the 5, and then it'll be -9 times the t. And again, t belongs to the set of real numbers. And then the last type of equation we're going to come up with is the new one, symmetric. And so for this one, we're thinking about taking these parametric equations and solving for the t variable. So I'm just going to rearrange this equation here. I'm going to bring the -1 over and add it to the x. And then I've got that coefficient in front of the t, -2, that I'm going to divide out. And that's going to be equal to, I'll do the same thing with the y equation. I'm going to bring the 3 over and subtract it. And then I've got a -1 multiplier in front of the t. I'll divide that out. And then same thing for the z equation. Bring the 5 over and subtract it. And then I've got a -9 multiplier in front of the t. I'll divide that out. And there is no t anymore, right? We've gotten rid of that parameter by setting the parameter equal to itself. And so I don't need that at the end here. I'm done. And so moving on to part B here, we're going to see a different type of situation. So for part B here, I've got the points P and Q. And again, my first thing I'm going to do is come up with a direction vector. I'm going to go P to Q, but you could go Q to P. So again, different people will have a different direction vector. And when I go P to Q, again, I'm starting with the Q coordinates and subtracting the P coordinate. And what I end up with here is 0, 2, and 1. And so we're going to take a look at my vector equation. Remember, for the vector equation, I get to pick either one of the points that was given to me. It does not matter which one you pick. Again, I'm going to pick the first one. And now I've already used the parameter t in this example. I know it's technically part B, but I'm just going to choose a different one to make sure it's really clear that this is a separate parameter. And I'm multiplying that parameter by my direction vector, which I calculated over here. And then I'll define that parameter as an element of the real numbers. Next up, we're going to do the parametric equations. And again, I'm just separating out the x, y, and z coordinates as I go through here. So x is equal to, taking the x coordinate -1, and then I'm going to have 0 times s. So x is just equal to -1. And then I'll move on to the next variable. Y is equal to, and this time I have 0 in the point, but I'm going to add 2 times s. So 0 plus 2s is just 2s. And then z, our last one here, is going to be 4. And then I've got 1 times s, so plus s. And again, here my parameter s belongs to the set of real numbers. Then we'll move on to our symmetric equations. Okay, so remember, to come up with the symmetric equations, what I do is I rearrange each of the parametric equations to solve for the parameter, so in this case solving for s. Now what I notice is I can't rearrange this for s, there is no s. Right? So I can't make it look like s equals some stuff. So what I'm going to do is just list this equation x equals -1 because it's just a rule. The x value is always -1 for this entire line. The x value is the same. So what I'm going to do is just list it at the end. So I'm going to rearrange the y equation to solve for s, and so I've just got a multiplier of 2 that I need to divide out. So I get y divided by 2 is equal to, and then I'm going to rearrange the z equation for s. So I just have to subtract over the 4, and I mean this is divided by 1 if you want to put it in there, but you don't need it. And then what we do, because we're just listing this other restriction basically on x, we're just going to put a comma between these two equations and say that the x value has to be -1. And that's a different look for our symmetric equations. We're used to, this is our typical symmetric equation where it's like three different pieces that are equal to each other, one with an x, one with a y, one with a z. This is always going to happen when your direction vector has a 0 in it. So notice that the 0 was in the x component, and then I have an x equals a certain number at the end. That's what's going to happen every time I have 1 0 in my direction vector. All right, we're going to take a look at part C. It's going to show us a different type of symmetric equation that might pop up. This part C gave us 2 points R and S. I'm going to do R to S for my direction vector. So I'm starting with the S coordinate and subtracting the R coordinate to come up with my direction vector. And I end up with 2 for the first one, right? That's 3 minus 1 is 2, and then I've got 2 minus 2 for the y component, that's going to be 0, and then 4 minus 4 for the z component, that's also going to be 0. So this example is going to be a little bit different because now we have 2 zeros in our direction vector. So let's take a look at what happens there. The first thing I'm going to do is come up with my vector equation. So R is equal to, and again I could start with either point here. I've got an R point that I could use 1, 2, 4, or an S point that I can use 3, 2, 4. It does not matter which one I pick. So I'm going to go with the first one because I'm boring like that. And then I'm going to multiply my direction vector by some parameter. I've already used T and S. I don't want to use R because that's the name of my equation. I don't want to use M because that's the name of my direction vector. I'm going to use K because I don't see it anywhere else in this example. Is basically kind of how we come down to that and multiply it by my direction vector. And then I'll just define that parameter as belonging to the set of real numbers. So next up are parametric equations. Again, separating out the x, so 1 plus 2k. The y, 2 plus 0k, so just 2. And the z, 4 plus 0k, so just 4. And here the k belonging to the set of real numbers. All right, so this guy's a little bit weird because the whole point of these symmetric equations is to rearrange so that I get different expressions in terms of, like, in this case, k equals some stuff. So I could rearrange the first one here. I would get x minus 1 divided by 2 equals k. But there's nothing else for me to set that equal to because I can't rearrange y or z so it looks like k equals some stuff. So in this case, the symmetric equations actually don't exist. And I'm going to find that this happens whenever I have those two zeros. And it doesn't matter where they are. It could be like the x and the z or the x and the y. All right, so moving on to the next example, we're going to take a look at 2 points. We're going to show that these 2 points, P and Q, lie on the line. So what do we know about the line? We know that the line passes through the point 2, -1, 4, and it has the direction vector -3, 0, and 5. So we're going to check both of these points and see if they lie on this line. I'm going to use 2 different methods to do that. That's why we're checking 2 points. So for point P, the method that I'm going to use involves parametric equations. And for either method here, I'd have to kind of think through the fact that I have this point that passes through. So my R naught is going to be 2, -1, 4. I can't use one of these 2 points because we're proving that they lie on the line. We're not given that. And I'm given the direction vector -3, 0, 5. So for point P, I'm going to use parametric equations. So my parametric equations, remember that's what I'm going to figure out what x, y, and z are equal to, and I'm just going through finding the x-coordinate of the point, and then I'm going to multiply a parameter by the x-coordinate of the direction vector. So -3, and I'm going to use t for this one. And then for the y-coordinate, or for the y equation, I'm going to come up with -1 plus 0 times t, so just -1, and then 4 times 5, or 4 plus 5 times t for the z. And again, t belongs to the set of real numbers. Okay, so once I have the parametric equations, we did an example like this already in 8.1. There just wasn't a z equation. To show that the point is on the line, all I have to show is that the t value is consistent. And it has to be consistent for all of the components. Now, in this case here, the y parametric equation does not have a parameter in it. It doesn't have a t in it. So all I have to do is check that point P actually does pass that, that equation, that y is equal to -1. So I'm going to start with that one just because it's a little bit different. So on point P, y does equal -1. I'm writing it down. It seems really obvious, but I'm writing it down because otherwise my teacher won't know if I thought about it. And next I'm going to check the t values in each of these. So I've got the x value for point P is 8, so I'm going to sub that in here. So I'm taking the x and I'm going to plug it in here, and then I'm going to take the z and I'm going to plug it in here. So 8 is equal to 2 minus 3t, and -6 is equal to 4 plus 5t. And then I'm just going to rearrange and show that it's actually the exact same t value here for both of these equations. So I'm bringing the 2 over and subtracting it, and then bringing the -3 over and dividing it out. And then over here I'm going to bring the 4 over and subtract it, and then bringing the 5 over and dividing it out. And what do you know? I got the same t value, and that tells me that P is in fact on the line. All right, for the point Q, we're going to use a different method. We're going to use symmetric equations. So both valid methods, you can choose. I wouldn't ask you for a specific one this year. Okay, so symmetric equations, if I'm coming up with those for the line, I do already have the parametric ones here, so I can use this to help me out. But you could also come up with the symmetric straight from the point and the direction vector if you were to sub it into that formula that we went over at the start of the note. So I'm going to just rearrange this guy for t, and I get x minus 2 divided by -3. I notice that the y equation does not have a t, so it's going to tag on to the end here. And then I'm rearranging the z equation to solve for t, so subtracting out the 4. And then I'll divide out the multiplier of 5. And these guys are going to be equal since they're both equal to t. So I've got my symmetric equations now, and I want to check the point Q. So I'm just going to write it down here again so you can see it on the screen. What I want to know is this symmetric equation satisfied? Now, since I don't know if it is actually going to be equal and I sub these numbers in, I have to separate the left side from the right side and then show that they're both equal to each other. So if you don't know that they're equal when you're subbing in, you have to separate. So on the left side here, I've got x minus 2 divided by -3, so our x value is -13. And I get -15 divided by -3, and the negatives of course become a positive, and 15 divided by 3 is 5. And then on the right hand side, I've got my z minus 4 divided by 5. Our z value is 29. We're trying to prove that the left side will be equal to the right side for this point. If it wasn't, then we would be saying that this point is not on the line. So 29 minus 4 is 25, and 25 divided by 5 is 5. And so therefore we've got left side equals right side, and so we do know that the point Q satisfies this first symmetric equation. We need to check the second symmetric equation. And what do you know, in our equation here, the y value is -1. So now that I've checked both pieces of the symmetric equation, I'll just write my summary. Since Q satisfies the symmetric equations, Q is on the line. And that's it for today's lesson. Enjoy your homework.